Good morning, everyone. Welcome to the Toronto Geometry Colloquium Season 2. This is a weekly series all about geometry processing.
This colloquium aims at promoting young researchers and researchers from traditionally underrepresented communities. Every week, we will have an opener talking about their cutting-edge research for 10 minutes, followed by a headliner giving us a keynote presentation.
Today, we are very thrilled to have Dr. Athina Panotopoulou as our opener to talk about tactile images for 3D shapes, and Professor Alexandra as our headliner to talk about her research on material design. If you have any questions for the speakers, you can write them either in the YouTube live chat or our Discord server. If you ask the questions when you have them during the talks instead of the traditional waiting until the end, it really helps us curate the best Q&A experience for all. So I ask you to please consider asking those questions. Our first speaker today is, as I said, Dr. Athina Panotopoulou, a recent PhD graduate from Dartmouth College, supervised by Professor Emily Whiting. Her PhD work spans many areas, mostly in non-photorealistic graphics, from tactile images that help convey shape information to the visually impaired, to watercolor woodblock printing. And specifically for this last work, I really recommend that everyone watches it. I have a big wide wall in front of me, and I just wish that she started a startup to sell these pieces of woodwork so I could buy like 5 or 6 of them. Today, she will talk about tactile images for 3D shapes. I'm very looking forward to learning what that means. Let us all give a warm welcome to Dr. Athina Panotopoulou.
Thank you. Thank you very much, Sylvia, for your nice introduction. I'm very excited to present my work to your community. From my understanding, your community shares the same passion with me about live shows and my passion for research. Today's show plays with geometry, image processing, stylized input, and fabricates computationally with fast prototyping tools. It allows for more accessible graphics and creative design from users. This work was the outcome of collaboration with Xiaoting Zhang, a postdoc at BU, Tammy Yu, a student at BU, Xingdong Yang, a faculty at Dartmouth College, and my advisor, Emily Whiting, a faculty at BU. And it has to do with tactile images that are felt with on a piece of paper by hand and are used by people with blindness. They can be found in places like museums, maps, or books. And Braille, which is a very well-known tactile alphabet, you probably have heard of it, is also very successful. In contrast, tactile images that represent shapes are not as successful. And this work tries to improve the design of these images by improving shape understanding from them. So we propose a new design for tactile images. The input is a 3D shape, and we output its tactile image, and we test shape understanding from this image by questioning human participants. So existing work in tactile images tries to improve their design, and many guidelines based on these findings have been made. But the problem with that is that they are very large documents. They cannot be easily learned, and they cannot be universally applied. So just to give you an idea, one of these documents is published by the Braille Authority of North America, or BANA, and we used to design the baseline images for our test study. And here you see an example of the image designed following BANA guidelines. So the left is the original image and the right is the corresponding tactile illustration. And I will discuss 2 elements that they are different from BANA and our design. So first, BANA suggests the use of semantic uniform texture. So one semantic area, the sepals, have one texture, while the petals have a different texture. In contrast to that, we indicate geometry with textures. Second, BANA suggests the use of one or more images taken from canonical viewpoints. This image is a canonical cross view, while the original image is a non-canonical view. So in this case, the eye level is not at the same level as the object level. In contrast to this, we design a single image which is a combination of multiple canonical views. And this is called multi-projection rendering. So closing the background material, I want to clarify that we present a semi-automatic way for a new design of tactile images made of laser-cut microcapsule paper and a user study that tests these images in terms of shape understanding. So first we ran 2 formative studies. With the first one, we tried to identify important information on shapes for the blind, while with the second, which I will discuss now, we identified common misconceptions on current illustration design. We gave 3D printed objects to 7 participants and 3 variations of illustrations. The first variation was taken from non-canonical or 3/4 views, the second one from canonicals, while in the third one, texture was added. And after that, we asked participants questions about the shape. For example, how many pieces has the back of the chair? The first observation is that participants found hard to use more than one image. For example, for the eyeglasses, they preferred to combine the 2 images into one. Also, it was easier for participants to understand viewpoints that have large surface area. For example, the side view of the rocking horse is preferable compared to the top view. Also, illustration of curvature is not accurate. For example, the non-canonical view gives a better indication of the shape of the teapot compared to the canonical view. So based on that, we designed differently than before the illustrations. The input to our pipeline is a 3D object given in its upright position and pre-segmented. With geometry processing, we use geometry and image processing to create a new illustration, a multi-projection line drawing, which we laser cut, and we 3D print corresponding objects to run a study and count how much efficient are these new images. So I will start with the placement of the cameras. We have a single master camera, which combines the rest of the cameras into one illustration. Here you see example of different camera locations on the left and the corresponding viewpoints on the right. If you remember from the study, we want to have all parts displayed clearly. So to compute these viewpoints, we use some attributes defined in the work of Secord et al., which give us the image on the right. And as you see, it displays clearly all parts, the handle, the main container, and the spout. The next step places the rest of the cameras called part cameras, and they are called part cameras because each camera renders a single part. Here we have 6 part cameras, 6 parts. I will focus on the spout. And from the user studies, we know that canonical views of large surface area are preferable. So we take into consideration the skeleton and the surface area of the canonical frame of the bounding box. And this gives us the image here. We repeat the same process for all cameras. And this is the camera placement for the faucet. And you see on the corresponding canonical views that the parts are displayed clearly. We then align the views with the master camera, following the information from the master camera. And we combine all the images together in a multi-projection drawing that you see on the right. From the studies again, we found that a curvature could be an indication, could be indicated with lines. So we create a curvature-based texture, which is from extracted cross-sections of the shape. And you see the textures here. So we extract for each part a texture, and after we post-process the image to make it more easily perceptible, following Banach guidelines. Then we test our design. So we choose 3 variations of common household objects, and the variations appear with the green. For example, the first chair here has a flat seat, while the second chair has a curved seat. And after we 3D print all 3 variations, and we laser cut the corresponding drawings, both following our design and Banach guidelines. And we give participants the objects for one type object. We give participants materials for one object at a time, the 3 object variations and the 1 type of illustration, and ask participants to fill both the objects and the illustration and choose which of the objects matches the illustration. We then repeat the same thing for all objects, and we consider correct the answer that when the participant chooses the correct objects. And after, we repeat the same exact process with the other type of images, so the baseline images, Banach guidelines. And for half of the participants, we reversed the order type. Now we'll present briefly the results of this study. The participants appreciated the use of single rather than multiple images and found more easily to identify curvature with the new texture. Here, the green represents success rate with our design and brown success rates with BANA guidelines. So the average success rate has doubled for the new design. And looking at each object individually, here you see the 3 object variations. Here we change the shape of the base. And the target object is the middle object always. On the top, you see the new design. So the new design depicting the target object, and at the bottom, the baseline design depicting again the target object. We see that it's much more successful with the identification of the V-shaped base with a new design. Also, curvature is very efficiently identified in this shape that has both a curved seat and a curved back, compared to the older design. The one design that higher success rate with the BANA guidelines is this one. The reason for the mistakes were 2. First, the earpieces appear to be of different shape, and also the headpiece appear to be of a single piece, while if you see here, it has 2 pieces. So part coincidence causes mistakes in identification. For this table example, we varied the legs both by changing the shape and by changing the number. A problem we observed is that in our illustration, one of the legs is fully contained within the tabletop, something that misled many participants to think that the design here is the 3-legged table. So we see again that limitation caused by part containment creates mistakes. So as a future work, I would like to improve upon these limitations that I just mentioned, and as well as make this tool accessible for the blind so that they can design on their own shapes and images. I want to acknowledge funding sources, organizations, and people that make this work possible. The organizers of the Toronto Geometry Colloquium. Also on behalf not only of me, but also my collaborators, thank you all for listening. And now I can sit back and enjoy Alexandra's talk.
Thank you, Athina. That was, I might say, a very touching presentation. I prepared that joke for a week. I'm very happy I said that. So we'll now move on to our headliners talk, and then we have a joint Q&A for both of them at the end. So remember, ask your questions to Athina now so that we can prepare the Q&A. Professor Alexandra Ion is an assistant professor at the Human-Computer Interaction Institute in Carnegie Mellon University. Her research trajectory reads sort of like a series of books focused on constructing new materials with different structure to have different prescribed functions. If you like those kind of extremely satisfying videos that you can see online of things behaving just perfectly and fitting just right into places and stuff like that, then you're really going to enjoy Professor Ion's research videos, which are featured on her website. Today, she will talk about unifying materials and machines, which sounds a little like the next cyberpunk game. So I'm really excited to learn what that actually means too. Let us all give a really warm welcome to Professor Alexandra Ion.
Well, hello, everyone. I hope you hear me and see my screen and slides and everything.
All good.
Great. So thanks so much for having me. I'm very much enjoying speaking at this venue because it's like really at the kind of intersection of where my work is. So I work on metamaterials or interactive structures. And so Sylvia already mentioned a little bit of my trajectory. I'm an assistant professor at CMU. My work is in HCI, where I also completed my PhD in, and then I moved on and worked with Olga Sorkin-Hornung at ETH in graphics. So my work is really grounded in digital fabrication, but what we essentially, we're just using those machines to make like cool new interactive structures. So why do we do that? if you think of traditional materials, you can think of wood or metals, stones, glass, whatever. Mostly you use the materials to build something, you assemble things, they're structural. Now, if you want to have a little more functionality, you might think of starting to, composite things together, like glue soft materials on top of rigid materials for safety in this example. Now, if you zoom into those, very common materials that every one of us knows, right? Rubber foam, it's very common. If you really look very, very closely, you can also see it with, just with your eyes. You see that there's like this open cell structure, which comes from air enclosements, just like as the manufacturing process of these materials. But what you can think of is that these are like a lot of beams that are just like randomly oriented. Now, the idea of this area of work that I do is that you take those beams, but you arrange them in a way such that they do something, more specific than just, being softer. So, in fact, just recently there was work on exactly this use case example where they have this lattice. This lattice assembly, very structured, very intentional how these beams are oriented in order to provide, better safety and better shock absorption. Now, taking this concept, you can go way further. You can create really materials that are ultra lightweight, as you see in the standalone example, that are noise canceling just by changing their geometry, that are light absorbing. And like this paint is called Vanta Black. Some of you might have seen this video, but I find it so fascinating that just by manipulating the structure of the material, it absorbs almost 100% of light. I believe it's 99.7%. So I find this very captivating. And the unifying theme here really is that all of this is made possible by carefully arranging the structure, so the geometry of the materials. Now, there's also really interesting and fantastic work, for example, by Christian Schumacher, where they looked at optimizing for localized elasticity throughout 3D objects, or even looked at manipulating the directional stiffness by creating, the geometry that achieves that. So there are also a lot of more interesting examples. So if you see this material, for example, the egg on the right breaks, but the one on the left doesn't. And that again is enabled by the structure of this material. So essentially what you have here is like this bistable structure that kind of flips over to its second state. And then as it goes in the second state, there is like a little area that is, people call negative stiffness, and that area traps energy. And this energy is absorbed from the falling egg, which is why it doesn't break. Now, another example of these geometries and what they can achieve is a very famous one, actually, I believe. And it's called auxetic materials, or, I like to describe them as volume changing materials. It makes them more graspable in a way. So as you see, like the person here just like pulls this material in one direction, but it actually expands in both directions. So thereby it can kind of inflate, if you so will, but still you have like a very simple actuation. It's a one degree of freedom actuation. So all of these examples that I just showed you, they are, well, I started with like the broader range of metamaterials, but we will focus on mechanical metamaterials, which are artificial structures with unusual properties that originate in their geometry rather than in the material that they're made of. Now, this is also true for other types of metamaterials like optical metamaterials or electromagnetic metamaterials, but we'll focus on the mechanical ones for the sake of this talk. Now, one thing that you might also have noticed is that most of these materials were really treated as materials. So well, traditionally, materials have been understood as materials. And what I think makes my work a little bit different is that I really think of them as devices. What can these structures offer us in terms of adding functionality, not changing the material properties per se? So I believe in this broader spectrum and in this broader embedding of metamaterials, which are a fantastic concept, I take just a little bit of a different perspective and think of, can we design structures that allow us to receive, sense input, process that input, and then in the end also create output. So I want to show you a couple of works where I kind of sampled that space, but at the same time, this is like a broad space, and there's a lot of geometry that we can design for. So it's there's definitely a lot of room for, well, hopefully interesting and inspiring discussions after this talk. So the first thing that we looked at was a kind of processing analog information, which you can think of as something that transforms the input into something else. So mechanisms do exactly that. They transform the input into some other set of output forces or movement. So you see in this door latch example that as the user is pushing down the handle, creates a rotation which causes these cells to shear, and they move the latch inwards. And that is how this whole mechanism works. So essentially, we have a grid of cells, and then each of those cells, this is kind of the vocabulary that we defined for this project, can have this topology. So rigid cells do have diagonals, whereas shearing cells don't. And this combination allows for a very controlled directional movement. So this is how an traditional door latch looks like. So it actually, what I want to point out is that it contains, it consists of a lot of different parts, including springs, which are kind of tough to assemble. And now, one of the main benefits of our approach in this case is that it only consists of one piece, which means that by virtue of only consisting of one part, there's no assembly, and thereby, because there's no assembly, you can create this as a part of a larger structure. You could print the entire door, including door latch, for example. And then the second obvious benefit is that, well, in mechanism design, essentially you have the design phase, which is also very tricky. And then you have the craft phase where you have to assemble everything. So we take that craft phase is kind of offloaded to the 3D printer in this case. And then for the design phase, we can assist users by creating, in this case, very easy to access online design tools where users have simple interactions, can do a tight design loop by also simulating their designs to see if they met their objectives in the meantime. While most of the examples that I showed so far are mostly 2D or 2.5D, there's no reason for not going 3D. So our editor actually fully supports that. Now, what else can we do than door latches? So here you have, you can see pliers that are strong enough to kind of lift things or tighten screws or things like that. Then this is actually my favorite example because it's somewhat unclear what it is. It's like a strip of material with some strange structure. But what it does is that it's kind of a copy machine, if you so will. So there are like two pencils embedded, and then the pencil kind of in the middle scales down your drawing as you draw. And then lastly, we also created this prototype of a Janssen walker to also showcase that you can, create robotic movement out of one piece with these types of structures. All right. Now we've seen a couple of applications, and applications also means that, you don't only have the structures, but you have the whole embeddings, there's a door around it, it serves some purpose. But if we kind of loosen that up, or take all of that away and just really focus on the, on the essence of what these mechanisms actually are, they are transformations. So if we only look at the motion paths that they kind of where the input is, where the user pushes down the handle, to where the output is, in this case, the latch moving inwards. Now, it turns out that even though the vocabulary is very simple, you only have these, essentially this a quadratic cell that either has a diagonal or not. It seems simple, but the design is still somewhat hard. And that is why we created a inverse design tool where users would specify the, the grid size, the movement, and then also draw a custom movement. And then what our algorithm does, it returns with kind of the cell assignment that best approximates these the transformation of the one motion path into the other motion path. So what we do here essentially, or what the algorithm does here essentially, is that, well, we take as input the grid size, about the grid size, and the paths that user defined. Then we analytically define some anchors out of the set of vertices that we have. And what we actually optimize for is this assignment of either a shearing cell or a rigid cell that best minimizes the distances between the user-defined paths and the paths that are the result of the current cell assignment of the current mechanism. Now, you might have noticed that we are still talking about these very distinct cell types, so a rigid cell or a shearing cell. Now, because we have this binary assignment of cells, we do have a very large search space, and we are kind of bound to combinatorial optimization. And so the question is, how can we best model this design space to find out, what is meaningful to look at? And I would like to just, state it right away that not all of the possible cell assignments are meaningful, because all of these examples, actually, if you look at the transformations between the paths, do implement the same transformations, so thereby are the same mechanism. So knowing that, we can move forward, and so this is kind of like the search space reduction that we were looking at. So here we can move forward and model the we identify these distinct mechanisms by modeling the structural constraints. So we create a constraint graph. So looking at just a single cell, we know that the shearing cells, the opposing members always stay parallel. And so we model that in the graph, where the arc is the parallelism constraint and the nodes in the graph are the edges in the cell. And so you see that we get two connected components for just one single cell, which models kind of like the different degrees of freedom that this cell has. Whereas if we look at the rigid cell, it has exactly the same constraints. So the opposing members still remain parallel, but then additionally the angles can't change of adjacent edges. So essentially, before we go into the optimization, we convert the cells, the cell assignments that we have from the geometric space into this like constraint graph. And here, by just propagating the constraint throughout the graph. And here we already see something interesting, that these blue highlighted cells, they are in the same connected component, which means that they are really constrained by their neighbors. Thereby, they cannot, like in theory, they would be allowed to change their angle, but they cannot because the neighbors prevent them from that. And so we know that these two cell assignments are really the same mechanism. And this reduces the search space quite a bit from a from the gray quadratic growth to the blue almost linear growth on the log scale. Now what we then do is to really optimize to create this to inverse design the cell assignments. We operate on the constraint graph where we merge and split connected components instead of just swapping kind of cells on the kind of geometric view of the mechanism. And well, throughout this optimization process, we use simulated annealing as a meta-heuristic here. Well, which then leads again to this, to this inverse design tool where users just specify their objectives essentially. So next questions in this type of mechanism, metamaterial mechanism design are, well, discrete optimization is just tricky because you might have observed in the search space, while we reduce it, it's still a large search space, right? So can we somehow apply continuous optimization? But the problem here is that it's a really nonlinear search space. So can we do like some approximation, rounding, whatever tricks to traverse this search space faster? Setting up a general theory for these aperiodic lattices would be something very useful, as that would lead to more real-time and general purpose material exploration tools. And then here I just wanted to point out that throughout this project, we did find some interesting transformations that were possible. For example, having a rotary input, but then that leads to self-intersecting output paths, or oscillating paths, or paths where you really smooth out entire corners. So looking at this on a more theoretical level would be a very interesting next step. So these mechanisms that I just showed you, they were absolutely analog machines. So what analog machines or analog devices have all in common is that they receive some input force, but then as the force kind of like traverses the structure, and that is also true for rigid body, like for traditional mechanisms, as it kind of traverses through all of these like little steps and links that you have in a structure, there's like some sort of decay at each and one of these steps, in this case, at each and every one of these cells, which leads to the output of that system being smaller than the input. So in this case, the latch moves in less than the user actually pushed down the handle. Now, what we did here is that we have, if we look at a close-up of this, really ugly print in this case of these metamaterial mechanisms, we actually designed the beam to not be just like a straight beam, but that one part is thicker, and then the other, the ends of the beam are thinner, just so we can enforce like a little bit more of hinging at the corners, which is what we want, and then the member part, the thicker part, should kind of just push the next cell further. Now, this thickness ratio gives us a stiffness ratio, because even though the member is thicker, like as it pushes the next cell over, it will still deform a little bit, and that is where this decay comes from. Now, if we just double this thickness ratio, which we could do by using essentially is throwing technology at the problem. So using higher resolution printers or multi-material printers, where the corners could be soft and then the members could be rigid material, that would already give us a pretty good stiffness ratio. Like, but just doubling the thickness ratio, we would get like a stiffness ratio of 64:1. Thereby, we can concatenate multiple, like more cells, and create more complex machines. Well, however, you can, like, even though 64:1 might sound really good, you just cannot get rid of this decay ever. I mean, that is just like how analog machines work. So obviously, the next logical step to do is kind of going from analog to digital, because there you don't have this problem of signal decay, and to kind of like explore the space of what would digital materials look like. And so we created these other types of cells, which contain bistable springs, similar as the ones that you've seen in this egg example. So they do have two stable states, this one and then this one that they're printed in. And so as you kind of push in the leftmost cell, that kind of snaps through to the other side, releases its own energy that it had stored. Remember the egg? It kind of like, that's the energy that that it absorbed from the egg is stored in the spring. So it releases the energy, pushes the next cell, that also releases its own energy, which pushes the next cell, and so on and so on. And so because at each and every one of these steps, you do have energy stored, you don't have energy decay, because they are just triggered, but they are not the force is not propagated. They're just like triggered, and then they release their own energy. So here it is in real time, where you see kind of how this signal, kind of progresses through the whole, cells in this case. And to kind of embed this in like some sort of usage scenario, we created this little lock where the user inputs a code at the beginning, and only if that's correct, everything or the signal will traverse to the very top, where it retracts those bolts that were blocking the door from opening. So you see that we already kind of combined the mechanism part and with the digital parts into one example here. So, there's like different things that you can do, like signal, like route the signal. Obviously, you will need that, but then also create gates. And we did model all of the important gates, and most importantly, the NAND gate. So we do have, we cover a combinational logic, and it's also time-independent logic, which makes this the current scope of this project a combinational circuit. Obviously, for the future, you would like to, move one up to sequential circuits where, you would want to have a clock signal. This is still a limitation in the current state of this project. And while there are also other people working on this type of mechanical computation in the meantime, there's still this problem of kind of how do you reset the springs back to their charge position where they store that energy, so you can do another computation step or configuration step. Depends on how you want to use this. And that would then, as soon as you can recharge the springs, you can create, you can have something like a clock signal maybe from the outside, and then also have like maybe some protected parts that are not affected by the recharging that can act as memory and so on. So I think the real power and benefit of this type of materials is not really to, to be a computer, but more that you can have a strategic way based on logic functions, essentially, how you can reconfigure your own material. Each and every one of these cells, they can transmit signals, but at the same time, they can also actuate another material that they're layered with, for example. So if you could also miniaturize this, you can think of kind of waveguides that can be reconfigured based on, maybe sensing something. So the next aspect that I want to touch on is kind of this notion of output. So this is, every one of these things that I showed you were kind of like a complete application. So obviously, the output in the door ledge example was the bolt moving inwards. But I wanted to kind of like take this notion and just like focus really on the output and what these materials could do as an output in this spectrum. So one way we approach this is looking at them as textures, where this door handle has multiple textures integrated into its structure, so it can communicate states like, well, I'm available, or as you move forward, you could be busy, or spiky means, well, please really do not enter. I'm not, I have something super urgent to do. And so how we achieve that is that, a global force folds all of these cells, but they are defined, there's a defined sequence to them. So first you can set it to go into this rippled state, which means, well, I'm kind of busy, but you can come in. And then only second, as you keep actuating this door handle, it goes to that spiky state. So thereby you can choose the states, but they are adding up onto each other, as you see here. But you can dynamically kind of traverse through these integrated textures into the material. Now here you see a different example of how these thinking about the output of these types of metamaterials is useful, as you can, for example, change things, not communicate to the user as the previous example did, but you can change properties dynamically, such as friction in this case. And one important aspect, here was for me to also keep the user interaction in mind. Like, how do you change the how do you change the state of your material? So this is not limited to the textures I've shown you here. You can create a variety of textures, and then as an outlook, again, if you can miniaturize these, you could have change your sandpaper in situ just as you need it. You can have dynamic you can have states in between that you choose as how you need them right now, or apply this notion of changing the friction, not to your shoes, but like to robots, that you can where you can change that friction maybe by applying those digital metamaterials that actually know when to change the friction of a robot. So one thing that, while we look at the space and like sample a couple of those, that we really looked at the function and what they should do, but we haven't really looked at how do we make them. So I mentioned in the beginning already that I mostly use these, mostly 3D printers just as a tool to, create these structures to have the tools create the structures for me, really. But there is an important aspect of how these structures are made, and the reason for that being that if they're hard to make, if they're slow to make, this really limits the real world impact that they might have. Why aren't these super cool new materials used today? So, and that touches on fabrication. So I really like this image of the, where the turtle is essentially, you can think of as the 3D printer. It's just very slow. But then if you think of laser cutting, for example, they would, laser cutting is kind of a pretty fast fabrication technique, which is really useful here. So, well, it's fast. And then additionally, it also gives you a good range of material selection that you also don't have with 3D printing. But of course, that's a 2D fabrication machine. So you are bound to constraints here if you want to create something that's 3D. And Sylvia knows very well, those are developability constraints where the Gaussian curvature should be 0 everywhere. Now, in developable surfaces, which is a very established but still very thriving kind of research discipline, people mostly look at recreating, approximating the 3D shape with 3D surfaces. So at the same time, I was kind of wondering, well, how about we look, why not the volume? I mean, the surface is cool and all, but why not the volume? So we kind of came up with this different type of metamaterial cell, if you so will, where we if you look at paper which has a very low bending stiffness, just by kind of curving it up, you get, obviously, due to bending energy, you get a higher stiffness. So essentially, this thing that you see here on the screen kind of became our new unit cell. So you might notice that this unit cell looks very different than the unit cells you've seen previously. But that is exactly also the point of this work, that if we want to design for different types of technology, then they might just look very different. So what these cells allow us to do essentially is, by changing the density of these ruffles, you also change the elasticity of the object locally. And also, obviously, they're very fast and easy to make. The connectors are already, they come with the strip of paper. You just fold them in, and and that was that. Like, you don't even need external fasteners. So to get there, we implemented an optimization tool, where in this case we use a cutting plane and then approximate that ruffle stack to approximate the 2D shape. And then essentially we just extrude it to fill the volume of the object that we just optimized it for. So in this case, the teddy kind of like has all of its torso and limbs and head made from single ruffles. And then, oopsie, let me see. Well, and then we essentially and then we export those ruffles to in a flat state, obviously, to be laser cut by the user. So this is the teddy in real life. So you see nothing collapses. And it's very, very springy. Now, the way we do that is that we have kind of two optimizations going on. So one is the inner loop, the ruffle simulation, which where we want each ruffle to deform smoothly. We base that algorithm on discrete shells. Then the connections of the ruffles should also meet in a smooth manner, which essentially means that their tangents should be the same. And then there should be, of course, no self-intersection. And to achieve that, we extend air meshes. And then, well, we sum up all the energies and use LBFGS to find a minimizer. And then in the second step, the outer loop, essentially, we look at, well, where are we at with the current ruffles that are, close to physically correctly simulated. And then only the outside of those, like the outer parts, like those, the more coarsely dashed lines. For those sections, we look at, well, how far are we from the actual, shape from the target? Well, if we're inside the shape, then we extend that portion and re-simulate again and do that iteratively. And then if we're outside of the shape, then we kind of reduce the length of that section. So we kind of push it back in order to, to approximate that shape. So the scope of this current project is really that we, as I mentioned, we optimize for the shape, so for this blue outline here. But as a next step, it would be, the next step is to really optimize for the forces, where you can define different forces on the boundary of that shape. So building on that shape, we also want to optimize for how much forces should they withstand. Which means that, from, in this case, we just kept the initial topology, or the topology was user-defined, and we only optimized that topology. In order to optimize for the forces, we will also have to optimize for the topology, meaning that, we would add connection points and so on. And then also currently, our tool handles only, well, it optimizes to, like, the ruffles are modeled as 2D curves and then extruded. But obviously, we would like to go more on a ruling-based approach and also optimize along 3D curves. And this is actually something that I find very motivating, and we're already working on. So we're looking into how we can use these types of ruffles, because essentially what you have is, like, you can change, you have a lot of springs that you can adapt. So that's exactly the point of optimizing for forces, such that we can, for example, create affordable passive prosthetics. In this case, we're looking at ankle prosthetics that are custom and are still very cheap to make, and therefore very accessible. Now, and then back to this notion of mass fabrication and real-world impact, which was kind of the motivation of this work. Is, now, okay, we looked at laser cutting, metamaterials. What are the next fabrication methods that we could look at? So molding 3-dimensional lattices, that's difficult, but interesting. Can we do stamping, thermoforming, whatever? Like, there's a long list of fabrication methods, and which ones are most beneficial for metamaterials, and how can we create geometry that respects the constraints of these fabrication methods. And then lastly, you can also think of, what about weaving? There are a lot of composite materials that are made by weaving that are ultra strong and so on and so forth. So, these are material properties that are interesting for us. And, can we create geometries that can use those types of materials as well? So to conclude, what I've essentially talked about was that metamaterials are understood as materials, but I think we can use these complex geometries and think further and think of them as devices, and then also try to integrate those types of functions that you need for devices. So why do we want to do that? Well, you can create, there's a couple of benefits that are just in general there for metamaterials, and then obviously would also translate to these devices. So they could be ultra lightweight, You can make them from one single material, therefore more sustainable to dispose. They miniaturize very well, which can also have medical implants or applications like that. And then also they have a definable lifetime, I would say, because there's no parts where dirt can be caught on. So you could actually compute how long that material will last because it only flexes, but it doesn't have many external factors that would influence its lifetime. So to get there, well, I see this kind of from an HCI perspective. As you've noticed, like I do care about applications and what we do with that, but obviously we need to have robust algorithms that create those complex geometries. Engineering is a big part of getting closer to this reality, and of course design. So I think I will just skip over this. Just know that design tools, as we can if we have novel structures, we need to have a way to compute that geometry. As we have more capability of creating geometry, we'll have more ideas for novel structures, and I think that they will always influence each other. So with that, I want to point out my shiny new lab website that you can go and check out for any details on this if you're interested, or reach out to me via email. So thanks so much for having me, and I'm looking forward to an interesting discussion.
Thank you, Professor Ian. That was a great talk. I was just typing the fancy website just as you were finishing speaking. We've gotten many comments, most of them a variation of "this is awesome" for each of the speakers. So now if you could please stop sharing screen while we have the Q&A. We'll have our first question for Athina while Alexandra can take a glass of water. So we've got many questions about the texture that you add to the material, to the image, I guess. First, you said that this texture represented curvature, and that adding this texture that represented curvature was a positive in your user study. I wonder if this is something you told the participants beforehand, like this is going to represent how curved something is, or this is something that they picked up intuitively as they were doing the test.
Okay, thank you for the question. So the way that we started this test study was by giving them one example of one of the shapes and giving them the solution. So I went over with them over this example. So I gave them, if I correctly recall, it was a teapot or something like a jug. So I gave them a jug and I gave them the texture diagram. And I explained to them how to interpret this diagram. So I told them, so you can see the shape, and you can see that the container of the teapot of the jug has a flower-shaped like container. And can you go over the texture and see how this fits with the actual 3D object? So I did this with the new design, and I did this also for the BANA guideline design. So I once again explained to them how to interpret the texture. So I told them, so for this jug, the main container has this texture. Can you see that it is different from the handle texture, for example?
Got it. Okay, that makes sense. So staying on this texture then, how do you decide where to draw, like in which orientation to draw the lines? Because like maybe this is like a binary ambiguity, right? But like, I don't know if it's curving one way or the other. I don't know which one is more intuitive. So like, is that a arbitrary choice you made, or is there some research?
Yes, actually, yes. Thanks again for the question. It is an arbitrary choice. So right now we haven't seen, for example, shapes that they have a different back from a front. So it seems kind of a symmetric shape. But yes, that will be maybe a bigger issue when we see that the cross section of the shape is not as symmetrical. So you are right.
Okay.
So I can, yeah.
Thank you. Okay, so now let's have our first question to Professor Ian. Well, I'll pretend I'm reading it as if someone said it, but really it's because you talked about developability, and that you must assume that I'm going to ask you something about that. So I wonder, and maybe the answer is just I should read the paper. Is it really the developability of paper that's giving you that behavior, like the thing that you showed, where you have the paper and the paper is like very flexible, but then you fold it and then it isn't. It feels like you're folding it on the same direction as, sorry, you're pressing on it on the same curvature direction as the one that it's folded. So I'd fail to see a little bit how it is specifically the developability property of paper and not, the fact that it's very flexible and cheap and many other properties that paper has that actually gives you that property.
Yeah, that's right. So there are two aspects to this thing. So one, the developability was really the motivation factor for this it's the speed up in fabrication. So it was really intended to, it's really about getting towards mass fabricable metamaterials. But then, that was just the property that this gave us that we could play with, was then the result of that was the elasticity that we can vary throughout the structure.
I see. Okay, so it's more about the mass fabrication that you care about in developability.
Yeah.
Okay, so another question for Athina is for the ones among us who are not visually impaired, things like symmetry and the difference between something being convex and concave are like very fundamental elements of how we perceive shape, and there's like a lot of perception theory around that. So I wonder if you've considered incorporating some of these concepts to your work, I guess.
That's another nice question. So symmetry is indeed a very crucial element, like a key element, a key information element, even for the blind. And I very, very lightly touched upon it when I discussed the result of the headpiece, the headphones, because the two earpieces appear to be of different shape. So they are symmetric, completely symmetrical. But in the drawing that we made, they seemed different. So it was not anymore a symmetrical shape. So that caused a huge amount of confusion in the blind, like in the people during the study. So yes, totally, it's a very nice direction of future work.
Right. Okay. Another question that we got for Professor Ian is: has there been any work on finding metamaterials for other physics quantities that aren't elasticity? So, for instance, thermal conductivity or electrical conductivity or things like that.
Yeah, there are a lot of waveguides and acoustic metamaterials, electromagnetic metamaterials, optical metamaterials. Maybe you've seen there's this image of kind of changing the refraction index. Like there's a straw in the glass, and then it would change. I think that's more of an image. Let me think about this. Well, yeah, there are many different metamaterials. I mostly focus on these mechanical ones because as a non-physicist, it's kind of, it's easier to grasp and also to fabricate.
Okay, makes sense. So I think you gave the asker a few keywords that they can look up if they want to see that word. So a question for Athina. In your experience in the user study, of all of the ingredients that you added, so you added this texture, you added this sort of special projection that you did, of all of the things that you added, what do you think was or did you test? What was the most important one, or what were the most important ones?
Yeah, I think, two of them were very important. The first one, the fact that you don't show all the shape from the same projection, because it's very important to see that it's very hard for us to understand that when you don't have vision, it's very difficult to interpret elements of vision. Like if you don't have it, it's just very, very hard to do it like on an image. So from that side, it's necessary that each part of the shape, it is shown clearly, and that means using different projections, so not to just take one view for all the object. And the second part is like the curvature-based texture, because you can use texture to indicate some information. And maybe for a different type of application, when you don't want, for example, to show to understand shape, or you want to understand something else, maybe texture can represent something different. So yeah.
Okay, thank you. That again, like every time you speak, I feel like I learn something new. It's been an amazing talk, so thank you again. Another question for Professor Ian. So your cells are square in the example that you showed of the first metamaterial. What if we extended it to other types of cells, like hexagonal cells, or even in 3D? You know, there's a whole variety of this. I'm asking because someone asked in the chat, and also because last week we had Dr. Alyssa Ross speak at our colloquium, and she showed how she optimizes over different types of lattices with different structures, and not just like square or cubic grids. So.
I mean, yeah, you can absolutely do that. And also, you know, in Christian's work, they had different, well, not only in his, like there were also follow-up works on that. They had different cells, and then, you know, either you pick them to have boundaries that fit well, or you kind of change those boundaries and then optimize for those changes to still represent the you know, the properties that he wanted it to have originally. For me, this is like, what I find interesting about it is if you combine things that are completely distinct, like, you know, just like from my work, if you take that bistable cell and the mechanical cell, well, the bistable cell exerts like very little force, whereas the mechanical cell, you know, the shearing cell needs more force to be moved, well, depending on how many they are concatenated. So kind of, you know, those relationships are something that I find very interesting, because that allows you to create more complex machines, as you can mix kind of, you know, parts that are functionally very different.
Okay, thanks for that answer. Let's ask our last question for Athina. This is a question from someone who just happened to see Professor Ian's presentation right after yours, and the question becomes obvious of, what if we wanted to represent motion to the visually impaired with that sort of texture? How would you add that? I guess it's the idea of going from image to video. How do you transmit video to the visually impaired? Like, what are the main challenges there?
It's a totally different application to create videos. So probably you will need many user studies to conclude to a nice example. One idea, for example, would be to use refreshable braille screens, but so far they are not in a very high resolution, so that to create video for the blind, at least with the blind people that I came in contact with, they were not very satisfied with the screen yet. Other than that, if you consider like just using the same material that I used to create video, in the sense of like creating a story like a comic book, like one image after the other, but still I don't think that will be very, very nice for them, because it's not as easy to explore a tactile image. So it takes much more time and much more focus and much more energy, rather than just looking at something. So looking, it's immediate. Touching it like takes a lot of time and effort. So I think that we need to use other like tools, materials than the one that I used.
Thank you. That's a good answer, and I guess it makes me rethink a lot of this new shift that we're doing towards video in a lot of our social media and our lives and all of that, and who it's leaving behind, I guess. So thank you for bringing this new perspective to this talk. So let's wrap up for the day here. Before we do that, we want to thank, there you go. We want to thank Suharu Ogawa, the artist behind this week's poster, and of course, our speakers, Athina and Alexandra. We will see you all next week at 3 p.m. Eastern, next Wednesday at 3 p.m. Eastern, sorry, to hear from Professor Theodore Kim and Zara Montazeri. Have a great day.